So, the ring. The ring is a bit more complicated than the previous two we've just studied for a reason. That is, we gotta look up both of the previous cases we calculated the electric field for and sort of combine what we learned from them. So the water reservoir and the, well, the ring itself, because for the disk, we will have to assume that the disk is made up of a bunch of rings that we can sum their individual electric fields and then combine them into the overall electric field for the disk. So, if you recall our previous video, you know that for a ring, E equals K, which I'm going to write down as 1 over 4 pi E0 times Q Z over A squared plus Z squared 3 over 2. So here there has been a mistake in notation. Actually, this is supposed to be A. Let me just fix this up real quick here. So this is gonna be A, and this is gonna be huge R. So the radius of the disk is capital R. Right. So we can go back to its origins and write down it can be pink, whatever. dE equals 1 over 4 pi E0 times dQ Z A squared plus Z squared 3/2. So now we got to do the water reservoir theorem, or the water container theory, which is that the density, electric surface density, equals dQ over dA, A being the area, not the length. However, we've got to expand a bit more. See, we're taking a single ring over here. The single ring, you can get a scissor and sort of cut it, and if it's bendable, a bendable material, you can sort of transform it into a line. So this ring, circle-ish, you open it and it turns into a line with height dA. Okay, so this is gonna get people confused, so I'm just gonna say the small r, okay? So this is dA and this is 2 pi A. So the density becomes dQ over 2 pi A dA. And then we can isolate dQ, so dQ becomes sigma times 2 pi A dA. And this is the Q, and then we can substitute dQ into the original equation over here. So dE is just equal to 1 4 pi E0 times Z times sigma 2 pi A dA over A squared plus Z squared 3.5. So these are the rings, so we got to integrate this monstrosity. I'm just kidding, it's not really hard. So integral both sides, the integral of dE is just E, and then that equals to, since this is a constant, I'm already gonna take it out, so it's gonna be 1 4 pi E0. Z is also a constant, so it comes out as well as sigma, so it's Z sigma. And then even though the 2 is also a constant, I'm going to keep it in for simplicity in the calculation. So I'm going to take P out. So that's the integral of 2A dA over A squared plus Z squared 3.5. So this is a, let me just tell you something real quick. Since we're summing up a lot of rings with like really thin rings, we can say we're calculating from 0 to R. So this is big R, capital R, because this is a defined integral. We're summing like every single ring from 0 all the way to R, okay? So it's a defined integral. So E equals to Z sigma pi 4 pi E0. And this integral here, you want to do this by substitution, really. So we're gonna call A squared plus Z squared RU, and if we do du dA, we're gonna find 2A. now we can say that dA equals du over 2a, and then we can just plug it in our original function. So this has become from 0 to r to 2a. So now dA is du over 2a, so it's du over 2a that multiplies u to the power of 3 over 2. Now dA cancels with dA, and then you have E equals z sigma pi, the fuck, pi with 3 fucking legs, 4 pi E0, and then a close integral of du over u to the power of 3 over 2. So this is a simple integral, which equals to, oh fuck, I think I messed up the audio accidentally, so maybe the audio is back to normal now. I don't even know if it changed, but anyway, so if you do this integral, we're gonna find that E equals z sigma pi over 4 pi E0, and then this is just gonna be minus 2 over u to the power of half, and then you evaluate it from 0 to r, and then we can substitute eu now to E equals z sigma pi 4 pi 0, and then this is gonna be minus 2 over u is a, right? But then we're plugging in the values already, so this is gonna be r squared plus z squared over half. Minus with minus becomes plus. It's like, so minus 2 over 0 squared is 0, so square root of z is just z. So we can rewrite this as being E equals z sigma pi, z sigma pi 4 pi E0, and then this just becomes, why there's a minus here floating around? That's so odd. What the fuck? 2z minus 2 over r squared plus z squared, like so. You can of course cancel out the pi's here, it doesn't really matter, so this becomes 4 E0, and then pi over here just goes away, and then you can rewrite density as being E equals z multiplies q over 4 E0 the area, so pi r squared, then 2z minus 2 r squared plus z squared, and a half over here, and my back, there we go. He calculated the electric field for the disk with the ring and water reservoir theorem, which is pretty interesting. Now on to the sphere that I talked about previously. I'm not going to prove it because it's, you know, complicated, but basically Newton proved through a bit of geometry over here that, you know, if you have a charged shell, then there's a charge inside it with zero that produces zero electric field, because you can prove through some basic geometry that this area over here produces as much force as this one and every single angle, so there is no if you put the particle there, it's not going to move. I mean, it is if you're gonna if you push it, but it's not gonna have an acceleration by itself. Right? So let me just can I make this a bit smaller? Oh, perfect. Now a bit bigger. Now a bit bigger again. A bit smaller again. I don't think this is gonna work. Yeah, no, because it's, yeah, but this is, yeah. So, by the law of the Gauss's law, which states that Q in over E0 equals to the double integral on the surface area of enclosed surface area of E dA, this is for me. This is my professor said this is going to be on the exam, so Luke, you gotta know this how to prove that inside the electric field is 0 and outside is given by something. So E inside. So what? We know already that as I explained previously, inside the force is 0. So E times Q is the force is 0. So this is got to be 0, right? So by definition, this got to be 0. However, as a vector, as a product of vectors, we can write this as EDA times cosine of 0. Why is it cosine of 0? Because if you take a surface area over here, dA always points outwards. It's a convention defined by our Greek god Gauss, dA. And the electric field is also this way, so the angle between them is 0, so the cosine of 0 is 1. And then you can say like, oh, EDA equals 0. Therefore, since the area cannot be 0, A is E must be 0. Therefore, it's proven. So this is just trivial stuff, whatever. Now, outside, it's a bit different, because outside we have the double S. Now it's no longer 0 because you can treat it as a particle. dA equals Q in over E0. All right, so over here, if you care to analyze that, we can do the same thing. E dA cosine of 0, which is just 1. Did I say 1 over here? No, I didn't, but cosine of 0 is 1, so whatever. Is 1. This equals Q in epsilon 0, so double integral the surface area of E in this case is a constant, so we can just plug it out. dA equals Q in over E0. So what is the sum of all these areas is just the surface area of a sphere, so it's E pi 4 pi r squared. So E, which equals Q in over epsilon 0, so E must equal Q in over 4 pi r squared epsilon 0. So E must equal Q in. Notice that this is Coulomb's constant, so it's going to be Q in K over RCC squared from center to center, because Newton also proved that you can treat this as a sphere, the sphere as a point, and so on and so forth. And you can do that stuff, and I don't have to prove it. And I think this is enough. He said that this question will be on the exam to prove this, so that's all I need to do. And thanks for watching. If there is anyone watching this.